So today we're going to take a look, an introductory look at logic. And as we take a look at this, some of this is probably things you've seen before. Some of it may not be. And parts of it also may be notation that you are not very familiar with, okay? So as we go through, if you have questions, please let me know. So to start with, a definition of a statement. A statement or a proposition is a declarative sentence that is either true or false, but not both. So when we say statement, this is what we will mean. So some examples of statements. It is raining. That's false, right? But we could say it because we can look outside and see. There are 11 students in modern geometry. That is actually true. Not today, they're not all here today, but it is a true statement. Angle A is a right angle, and that would be a false statement from the picture that I've drawn. That's angle A. So those are all statements because I can say true or false. These are non-examples. All three of these are not statements. Is it cloudy? We would typically call that a question. 3 minus x equals 4. Why is that one not a statement?
Because it can be true or false.
It could be true or false, either one, depending on what x is, right? So it depends. We would call that a conditional sometimes. It's a condition upon what x actually equals. And the third one says construct a rhombus. What do we usually refer to that as when we talk about a state or a sentence like that? A command or an imperative, exactly. So that's not a statement either, okay? Remark. We use propositional variables. That's what that x was. I'm sorry, not what the x is. Such as p, q, and r to represent propositions. These may be joined together to form compound statements. So like on the previous slide where I said, it is raining, we would call that letter P or Q or R or whatever letter we like. But it's a shorthand way of representing it, kind of like we use a variable x often as a shorthand way of representing a number or numerical value that we don't know. A negation is the logical opposite of a statement. If we say that the statement is P, then the negation looks like tilde P. So it kind of has the feel of it like a negative, right, in front of a number, just by its form. And we would read it in one of a variety of ways. We can read it as the opposite of P, the negation of P. And we're going to find the negation of a very straightforward sentence right now. I am rich. Okay. What would the negation of I am rich be? I am not rich. Thank you, Shana. And that's very good that you just put the word not in instead of changing it to poor. You don't have to be rich or poor. There's something in between. Most of us are probably something in between, right? So be careful not to overdo your statements. Change as little as possible. So simply putting the word not in there is actually correct. I am not rich.
Would the other work though?
It wouldn't, because the opposite of I am rich is not I am poor. All right, it just means I wouldn't be, whatever the category is that you put rich into, I fall slightly below it in terms of monetary value or whatever we're measuring. So yeah, it would not be correct.
But for like all students are rich.
Oh, we're going to get there in a second. Yeah, hold tight on that. There's a couple of ways we can connect statements together. One of them is with a conjunction. A conjunction is the equivalent of an and statement. So for example, if we had the statement we had before, I am rich, and we also have a statement, I am awesome, What do you think it would sound like to create the conjunction of those two statements? Exactly. We're just going to put the word and between. I am rich and I am awesome. Now, the notation that you'll see written right there that joins them with the P and the Q looks like an upside down V. Okay? So a conjunction is represented by an upside down V. Sometimes I have students that think, well, it kind of looks like half of an N for and. The N's in the middle of and. Whatever it takes to help you remember it. A second type of way that we can combine statements is with an or statement, or it's called a disjunction. So if I use the same P and Q that I have on the screen right there, I am rich, I am awesome, what would the disjunction formed with those two statements be? Very good. I am rich or I am awesome. And you'll see the notation on the left is that when we use an or statement or a disjunction, it does look like a V. Okay, so the sign flips upside down. And is an upside down V, and or is a V. Okay, so what I'd like to show you next is a way to construct a logical table for whether statements are true or false. These are called truth tables. Anyone who's helped my number theory students or contemporary math students potentially, depending on which section of contemporary math they've taken, may have seen these. They're used before. We're going to do truth tables for negations, conjunctions, and disjunctions. So to start with, we're going to do negation. What we're going to do is we're going to create a 2-column truth table, so just like a, almost like an XY chart. If my statement is P, then its negation we looked at is tilde P. So now think with me. If you had a true statement, if it was true that I am rich, then the statement I am not rich would be what? False. Exactly. And if the statement I am rich is false, then the negation I am not rich would be true. So negations are really straightforward. All we have to do is to switch the T's and the F's, the truth and the falseness of the statement. Conjunctions and disjunctions get a little bit more complicated because we're comparing two statements, right? So when I'm doing conjunctions and disjunctions, I actually need 3 columns as a minimum, 1 column for P, 1 column for Q, and then the column that combines them. A conjunction is the upside down V, so it's P and Q. And my disjunction will look very similar, but it will have an or column instead of an and column. Like so. Okay, so let's talk about what our options are for the truth and the falseness of these statements. So if I have a statement P and I have it being true, it could also be that statement Q is true, right? They could both be true. But if statement P is true, it could be that statement Q is false. But maybe I don't have any possible truthness to the statement P. I'm just not rich. I mean, because that's what P was, right? So that one's false, but maybe I am awesome, so that's true. Or maybe they're just both false. And wouldn't that be a bummer? Not rich, not awesome. What do I do? All right, so if you have an and statement, so if I make the statement, I am rich and I am awesome, the only way that that is a true statement with the and inside is if both statements individually were true, which is the first row of this truth table. If either piece of that ends up being false, then if I come in and I tell you I am rich and I am awesome and you happen to know that I'm not rich, then that would be a false statement. Or you happen to know that I am not awesome, that would be a false statement. Or maybe you know that she's really neither one at all, well, that's also then a false statement. So the only way that you get a true statement from a conjunction is if both statements individually are true. Now here's the cool thing about truth tables is that the first two columns are the same every time you do them, because these are the only four possibilities when you're comparing the two statements. Okay, true, 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 false, false, true, and false, false, which means that as I do my disjunction, the first two columns look the same. True, true, false, false, and then they alternate. Or statements are different. If I come in and I tell you, I am rich or I am awesome, when would it be possible for that statement to be a true statement? When either one is true. What if both are true? It's also true. It sounds funny to use the word or if they do that, but it would work. So with an or statement, anytime individual statement, one of them or the other one is true, the whole thing's true. So then the only time it's false is if both statements happen to be false. So this would be what our disjunction truth table would resemble. Any questions on those? All right. Negations of compound statements. So negating statements that are compound is a little bit different. When we did the single statement, right, I am rich, all we had to do was drop the word not in it. And they're not always that straightforward. We'll talk about those a little bit more later. But for a compound statement, it becomes a little bit more complicated. So I have two individual statements. And if the statement, I am rich and I am awesome, is a true statement, what would I have to do to make it false?
Make both of the individual statements false.
Would they have to both be false?
Or no, make one of them.
At least one, right? So I'm going to take each individual statement, I'm going to rewrite it as though it were false. So I'm going to write, I am not rich. And I'm going to leave a space for a moment. And then I'm going to write, I am not awesome. Right, there's a space in between there. So Noah said, I want to make both of them opposite, which I've done. But the question is, does the word and still reside between them? Do they both have to be false for the statement to then actually be false? No. I actually can put the word, and would and should put the word or between them. Because if either of the individual statements is false, it's going to negate everything, right? If all of a sudden my wealth goes out the window, I am no longer rich and awesome. I'm just still awesome. But I don't get to use the word and in there. So this is what it looks like notationally. You see the tilde out in front, negation, right? And it's the negation of the individual, or not the individual, but the compound statement as it began, P and Q. Now you might notice that we changed three things, right? What we really did is we negated the first piece, we changed the and to an or, and we negated the second piece. That's the process that we actually went through. So that's a negation of a conjunction. Now we're going to do negation of a disjunction. So this is the disjunction, I am rich or I am awesome. So what do you think is going to have to be the opposite? I mean, what am I going to have to do for the negation of I am rich or I am awesome? What would actually have to be changed to make it the opposite of this statement? You got it. I actually need the negation of both. I am not rich, I am not awesome. And it's an and between there. Because if either one of them were actually still true, like if I were rich or if I were awesome, then I would actually still have the original statement being true. I have to negate both pieces at the same time to have an or statement be false. So the notation again for that would have the tilde on the outside of the P or Q notation. And again, if you'll notice what we did individually is we negated the P, we negated the Q, and we changed the or to an and. Now these two, I probably should mention, you've probably seen this before, but the triple right here, that means logically equivalent. Okay, so it is like equals in mathematics, but we use this symbol for logic instead. Oops, my bad. This right here and this right here, when we take those two pieces and we consider them together, those actually are credited to a gentleman by the name of De Morgan. They're called De Morgan's laws. So this slide is not any new information. It's just categorized so you can see that he kind of gets credit for it. These are De Morgan's laws. So when I teach this in my number theory class to the students who are going to be elementary and middle grades teachers and so forth, we talk about the fact that there's three pieces, P, the and, the Q, and they all change, right? The P changes to negative P, the and changes to or vice versa, and the Q changes to negation of Q. We change all three pieces. All right. A predicate or a propositional function produces a proposition that's either true or false depending on the choice of X. And we saw one of those when I gave you the non-example earlier. I don't remember what my equation was, but it had an X in it, something like 3 minus X equals 5 or something like that. And we couldn't say it was true or false because it depended on what X was. So that's called a predicate or a propositional function. And another example of that would be 3 minus X is less than 1. All right, so something that Kennedy mentioned, she sort of started to ask the question about it, and I said, I promise we'll get there, is what we're hearing next. The universal quantification of a predicate for all x, p of x is true. So there's some notation here. Depending on what math classes you've taken before this one, you may have seen the notation, you may not have. The upside down A means for all. Sometimes you'll see a comma between the for all x, p of x, and sometimes you won't. We're going to get to English for what this is doing in a minute, but I just want to give you some notation first. Here's a statement about it. For all triangles, got that for all in there, for all triangles, a squared plus b squared equals c squared. All right triangles, sorry, I wrote it, I didn't say it. For all right triangles, a squared plus b squared equals c squared. Of course, given that a and b and c are identified properly, that matters, but. Okay, so this is statements that are always true. The universal quantification are the kinds of things that your mama told you never to say, right? Never say never, right? When you say something like, you never da-da-da-da-da, it's probably a false statement to begin with, right? Or you say, you always, yeah, that's probably not good either. So those really strong words are universal words. For all, for every, never, none. All of those are called universal quantifiers. Existential quantification of a predicate is that there exists an x so that p of x is true. You know, this is that one time when you fill in the blank. Maybe you fill in the blank and you did something you're supposed to do, or maybe it was something you wasn't supposed to do. There exists a time. It happened at one point. There exists looks like a capital E, the boxy one, backwards. That's what there exists looks like. So this is there exists in x, so that p of x is true. And for an example of this, there exist quadrilaterals that are squares. Yeah, no problem. We agree with that. There exist quadrilaterals that are squares. All right. When we negate things with quantifiers, it's not as easy as simply plugging the word not into the sentence. I'm rich, I'm not rich. No problem. We can put the word not in. But when we have these quantifiers, it becomes more difficult. So logic rules say something like this. The negation of for all x, p of x. So think about what would happen if we gave it an example. So if you say, every time you come home, you leave your shoes in the middle of the living room floor, which I'm sure I've said to my son before. I'm sure of it. Well, what does it take for that statement that I just made to be false? One time. There exists. All it takes is one time for the child to not take his shoes off in the middle of my floor. So it's equivalent to having there exists an X where the following didn't happen. There existed one time when he took his shoes to his room, or maybe he left them in the car. I mean, I don't know. But they weren't in the middle of my living room floor. All it takes is there exists. So anytime you have a universal quantification and you negate it, it becomes an existential quantification. And vice versa. If we start with an existential quantification and we negate it, it will become a universal quantification. Rules of logic are really nice and symmetric. Lots of symmetry going on here with our arguments, so that's very nice. I think I have an example next. Let's see. I do. We're going to find an equivalent statement to this one. So the it is not true at the beginning is the equivalent of having a tilde up here, okay? So we're trying to negate this so that it doesn't have the statement it is not true at the beginning. So what would the negation of all students in modern geometry are girls be? Right. There exists a student. All it takes is one. There exists a student in modern geometry that is not a girl. So these two statements are equivalent because I've removed the it is not true from in front of it, of course, right? And created a statement that sounds, number one, more grammatically correct for English, doesn't it? All right, let's do one more. Oops. Equivalent statement. So write down what you think it would be, and then we'll share out loud. It is not the case that there exists a triangle with four sides. What would the equivalent statement to that be? Just write it down for a sec. English grammar-wise, this is an awkward way to say this. So what did you write down for an equivalent statement?
All triangles do not have four sides.
Perfect. All triangles do not have four sides. It's almost like he read it off my screen, but he didn't. That's right. All triangles. So there exists became all, and then we negated the second piece, triangles having a triangle, four sides, and not having four sides. All right, there is one more way that we can compare or combine statements together, and that's with something called an implication. Oh, there's one more. I'm sorry, I forgot about that. There's one more way to write this. No triangle has four sides. Did anybody write that down? That's what you had written down? Yeah, so we didn't talk a lot about this, but these, I said it, these are both universal quantifiers. They both have that sort of like all or nothing mentality to them. So this would be another way of saying it. All triangles do not have four sides, or no triangle has four sides. Okay, implication. An implication is an if-then statement. So an implication for a conditional statement has the form P arrow Q. P is called the hypothesis. Q is called the conclusion. And all of these are ways to say this in English that mean the same thing. If P then Q, P implies Q, Those are the two we'll use the most frequently. P is sufficient for Q. Q is necessary for P. P only if Q, or Q whenever P. So any of those phrases that you see, you're looking at an implication or a conditional statement that means if P, then Q. So we're going to find the implication P implies Q for the following. It is raining for P, and Q is it is cloudy. So if I use the statements it is raining and it is cloudy, what would the English statement look like if I wrote out the if then or implication statement? What's a possibility?
If it is raining, then it is cloudy.
Good deal. If it is raining, then it is cloudy. Now, is that the only thing that we could write down? No, we just had a slide over here with like 6 other things or something like that that we could write down that would all mean the same thing too, okay? But this is probably the most straightforward one, to say if the first piece, then the second piece. So it would sound a little bit awkward in English to say it, but we could say it is raining implies it is cloudy. We don't really talk like that, but it would be true. I mean, like that would work. Some of the others, the same kind of thing. Converse and contrapositive. A converse of P implies Q is Q implies P. So if you switch the order around, so like on the one above, if we did the converse, what would it be? Yeah, if it is cloudy, then it is raining. The contrapositive not only switches the order around, but it also negates things. So again, if we did the negation of the one above, what would it be? Or if we did the contrapositive, I meant to say. If it is not cloudy, then it is not raining. Exactly. Sorry, I thought I had that at the bottom of the screen. I obviously don't. So it's important to realize that those are not necessarily the same statement, all 3 of them. So we're going to find the implication, the converse, and this should say contrapositive. I fixed it on another slide. And the contrapositive of the following. Every square is a rectangle. Now, the first thing to be realizing that is that this is certainly an implication, but it's not really written in an if-then form. When it says to do the implication, that's what it's referring to. So if I were to do the implication and I were to rewrite this in if-then form, what would it look like? How might you rewrite that to say if something, then something else?
If x is a square, x is a rectangle.
Okay, if x is a square, x is a rectangle. So I have something very similarly written down. There's the right one there. If it is a square, you used x, I said it. If it is a square, then it is a rectangle. That would be my implication. What would the converse look like?
If it is a rectangle, then it is a square.
If it is a rectangle, then it is a square. That's the converse. What would we get for the contrapositive? You got it. If it is not a rectangle, then it is not a square. Now, I said just a moment ago that these are not all 3 the same statement, but 2 of them actually are. An implication is equivalent to its contrapositive. So if that implication, if it is a square, then it is a rectangle, which is a true statement. Squares are by definition rectangles. Likewise, I could use the statement, if it is not a rectangle, then it is not a square. And those 2 mean exactly the same thing. But the converse does not. If it is a rectangle, then it is a square. That's not a true statement at all, actually, right? So that one's a really good example of where it all kind of falls apart if you try to think that one means the other. And people do this in logic all the time. Listen in everyday language and you'll hear somebody do something where they use the converse and think, oh, well, then this is, no, it doesn't work like that. So think about it. All right, we will stop there for today.